So continuing on to more geometrical type definitions. Today we're going to deal with the moment of inertia. So centroid mathematical definition took x times the integral. Moment of inertia is basically x squared. What it does essentially is it is a measure of how hard it is for something to be rotated. So in the three-dimensional sense, it's the rotational version of mass, really. It's how hard or how much effort does it take to rotate an object. We're going to be staying in 2 dimensions for now. We'll deal with the what's called the mass moment of inertia next class. That is the three-dimensional version. But today we're only dealing with the 2-dimensional version, which is just a geometrical construct. So there's no sort of mass involved with this. It's just devoted simply to the geometry of the object, the area of the object, where it is in space. And so again, official definition of my moment of inertia. And this is going to depend on which axis. So again, if I'm thinking about this as a resistance to spinning, this object could either spin around the x-axis or it could spin around the y-axis, and those should be two different efforts associated with them. So Ix, the resistance is spinning around the x-axis, Iy, resistance is spinning around the y-axis, and that depends on essentially the distance from each axis. So for Ix, I have y squared as the distance to that little element dA. For Iy, I have x squared as the distance to that element dA. So again, perpendicular distances integrated over the entire area gives you the moment of inertia in each of those two, or over each of those two axes. There's also a third one called the polar moment of inertia in 2 dimensions. So the polar moment of inertia in this xy 2-dimensional plane is essentially equal to the rotation about the origin. Technically the rotation about the z-axis at any point, but it's usually the origin. So again, usually a subscript down here telling you what point it's actually around, and that point usually being O for the origin. If you are dealing with the origin, then the distance, perpendicular distance from that origin to my point dA is just some distance r. And then standard kind of geometry Pythagorean theorem, r squared is x squared plus y squared. So if you think of it that way, I take the integral over r squared dA as the definition of the polar moment of inertia, but r squared is x squared plus y squared. And so integrating x squared dA gives me Iy. Integrating y squared dA gives me Ix. And so the polar moment of inertia is the same as the two moments of inertia about each axis, Ix and Iy, added together. And so like we had for centroids, there's also tables of common shapes and their associated moments of inertia. So instead of having to do those integrals, many of them have been done for you: rectangles, triangles, circles, half circles, ellipses. And so we can just use these tables to find the appropriate equations for any of these easy shapes. One thing that's slightly complicated for these is that the moment of inertia really depends on the axis, because the moment of inertia integral of distance squared dA really depends on how far away your object is from that axis. So for example, if I'm looking at this rectangle here, it's going to be harder for me to rotate this rectangle about the x-axis than it is about the x prime axis, x prime going through the centroid. Because again, if I'm looking at distance perpendicularly to the x-axis, this is a much bigger distance. And so that being squared gives me much harder rotation around x than around this x prime axis, where there's only half the distance. And so essentially a factor of 4 when I square half the distance. And so you'll see from the equations, a moment of inertia about the x-axis is 1/3 base times height cubed. So base along the x-axis, height perpendicular to it. So 1/3 base times height cubed around this x-axis, but only 1/12 base times height cubed around the centroidal x-axis. And similarly for the y directions, y-axis, I have 1/3, this time base cubed times height, because again, that's my perpendicular distance is now the base when I'm dealing with the y-axis. So that's the distance I care about. So that one is the one that gets cubed. And similarly for my y prime axis, 1/12 for that guy. And then same thing for the triangle. I have a value for Ix about the x-axis, which is down at the bottom of the triangle. Or similarly, I have a I bar x prime, the moment of inertia about the centroid. And so one thing about these tables is make sure you know which axis you're dealing with and which axis corresponds to the problem you're dealing with. Am I taking the moment of inertia about this bottom axis? Am I taking it about the centroid? Is it the x-axis? Is it the y-axis? So be very careful with those. Luckily, this book is fairly good in terms of its denominations, in terms of Ix is the x-axis, I bar x prime is the x prime axis, also puts a bar over the I to remind you this is the centroidal moment of inertia about the centroidal axes. Also, it gives you a figure that you can see where all these axes are and where they all line up. So this, again, a very good table for these. Some tables aren't quite as nice, but again, have the same thing for the circle. So circle I bar. So in this case, my x and y axes are actually through the centroid of the circle being right in the middle. So again, bars on my eyes indicating centroidal moments of inertia. Also using the polar moment of inertia in this case. Same thing for semicircles, quarter circles, and ellipses. So simple shapes, there's all my moments of inertia. Again, just make sure you're using the right one. Another thing you may be dealing with, not necessarily so much in this class, but definitely in one of your later classes, mechanics and materials, you're going to start building things, building beams, building things of that nature. And you're going to want to know properties, specifically moment of inertia for your building materials. And so if you're building out a 2x4s, you're basically looking at the cross-sectional area. So cross-sectional area of a 2x4 is a rectangle, can use the rectangular moments of inertia we just saw. But you might also have things made out of steel, in which case there are steel I-beams, which are either W shapes or S shapes. You could have channel shapes, so C-looking things, L-beams, L-brackets, things of that nature. And so a lot of these are very standardized in terms of their designations. And so they're built to specific sizes. And because of that, people have already calculated moments of inertia for these things. And so again, for these W shapes, you see I have my Ix bar. So again, through the centroid, moment of inertia. So rotation around my x-axis, Iy bar, rotation around my y-axis, moments of inertia for all these different variations in terms of their depth and width and sizes. So those are handy tables to have as well. And now a lot of times in these tables, you're only given one value. So again, we saw in the previous table, the only values for Ix and Iy were the centroidal ones. In the table before that, the rectangle and triangle had non-centroidal ones, but primarily most of the moments of inertia you're given are through the centroid, mainly because that is the most useful. The reason why it's the most useful is we have something called the parallel axis theorem. So if you want to know the moment of inertia about an axis that's not the one given in the table, you can actually find it through this theorem. Parallel axis theorem says moment of inertia of any area with respect to an axis is equal to the moment of inertia of some parallel area, parallel centroidal axis, and then plus the product of the area times the square of the distances. So essentially, if I have some centroid, so this is some weird shape. For some reason down here is a centroid. So I have some centroidal axis x prime. And when I looked that up, this weird shape in my table, it gave me the moment of inertia from it. And then to find the moment of inertia for x, this axis down here, all I need to do is take whatever moment of inertia I found for x prime, and then add the area of the shape times the perpendicular distance, in this case dy squared, and that will give me the new moment of inertia about this new axis x. And so mathematically, my new moment of inertia, I, is my old moment of inertia, IC, plus the area of my object times the distance squared. And again, this distance is the perpendicular distance between the two axes, between this axis and that axis is what this D represents. And generally you have this, it works for any sort of geometry. So whether I'm dealing with an x-axis or a y-axis, it all works. So if I have the x centroidal moment of inertia for some object, and I want to know the moment of inertia about some other x-axis, so some parallel axis to the centroidal one, I just take the one that I know, the centroidal one, and add to it the area of my object times, again, that perpendicular distance between the two, d squared, d being in the y direction. Similarly, I can do that for the y direction, take the y centroidal moment of inertia and add the area times the distance, in this case in the x direction, again, still perpendicular. So a couple things that I want to make perfectly clear on this. This guy right here needs to be the centroidal axis. It does not work if that is not the centroidal axis. So if you ever need to go between one axis and another axis and they're not the centroidal ones, so if I have some axis down here that's x1, some other axis up here that's x2, and I want to know the moment of inertia of this guy, x2, based on the fact that I already know x1, I can't just take this distance squared. What I need to do is essentially take this x1, take it back to the centroidal moment of inertia using that distance, and then from the centroidal moment of inertia, I can then find x2 or ix2 based on this distance. And then as I mentioned from when we looked at the tables, make sure you're using the right equation for the right situation. If you need a centroidal moment of inertia, make sure you're using the centroidal one. If you need a y moment of inertia, make sure you're using the y moment of inertia. And again, in the good tables, like the one we saw, you'll see a figure so you can kind of match up x prime, y prime, I bar, what exactly you're looking for. So another property that's defined with moment of inertia is something called the radius of gyration, usually called k. And so k is defined to be the square root of the moment of inertia divided by the area. If we rearrange this equation, we can see that the moment of inertia is given by k squared times the area. If you remember the definition of moment of inertia, I'm integrating some distance squared times an area. So essentially what I'm doing is I'm taking the average value of the radius squared. And so the moment or the radius of gyration is kind of equal to the root mean square of the average radius. I guess root mean square is average. So it's the root mean square radius for whatever object I'm dealing with. So that's kind of the physical representation of what the radius of gyration means. But if I know the radius of gyration, it's fairly simple calculation to find the moment of inertia. And then finally, just like we've done a few times, for things like centroids, if I have a composite shape, so I have some object that's made out of a bunch of different other shapes. So for example, those I-beams that we just saw, I can make those out of 3 rectangles. So one rectangle up and down in the middle, then 2 horizontal rectangles, top and bottom. I can calculate the moment of inertia of that by doing the similar thing to what we did for centroids. So take the moment of inertia of one object, then find the moment of inertia of the second object, and kind of add them two together. One big complication that we didn't have for centroids is that when I do that for moments of inertia, I have to make sure when I add them together, everything I add together is about the same axis. So I want to make sure that if I'm using the centroidal axis, all my moments for all my little itty bitty parts of this are all about the centroidal axis of the entire object, or all about the bottom axis of the entire object. Whatever it is, whatever axis I'm trying to take this around for my big, large object, all my smaller parts should be relative to that big axis that I care about. And so obviously that's where the parallel axis theorem comes in very handy. And so as usual, in class today, we will see examples of all those scenarios.